This program is brought to you by Stanford University. Please visit us at stanford.edu.
I'd like to draw your attention to a couple of future dates. First of all, going around with a clipboard today will be a poster for next week's seminar, which actually follows the theme in many ways of today's, although in a manner that might surprise you, so come along to that. That will be called Using Behavioral Sciences to Address Climate Change and Energy Security Issues. Will be presented by Carrie Armel, who has activities both in Freeport Institute for Energy Efficiency as well as Stanford Prevention Research Center, which is in the School of Medicine. Following that, it's important that you know that the energy seminar the week, 2 weeks from now, will be on a different date, on a different occasion, and Lee will tell you about that.
Yeah, you'll see these posters going up, and I'm going to pass them around and ask those of you if you're willing to help us put them up around campus. Just take one or two and take them back to where you are. It's called Sustainable Places, and it's about how people are walking the sustainability walk. And so we have two panels. One is on private leadership, called The Business of Sustainability, with Christina Page of Yahoo, Joe Stagner, who's the new Executive Director of Sustainability and Energy Management here at Stanford, Jim Sweeney and Peter Williams from IBM, and both Christina and Peter have similar functions to Joe at their respective companies. And then Felicity Berenger is going to be the moderator for the second panel, which includes Gavin Newsom, Larry Goulder, Diane Greenwich, who's one of the commissioners of the California Public Utility Commission, and Mary Nichols, who's chairwoman of CARB, that's implementing AB 32. So it really should be a blockbuster day. It's on a Tuesday from 1 to 4. And also, GSEP is going to be celebrating their 5-year anniversary. Lynn Orr's here. He'll be giving this on Monday from 3:30 to 5:30. And I'm not sure where, Lynn?
It's in the big lecture hall at the Hewlett Teaching Center.
Okay. And Lynn will give an update on what's happened so far with GSEP, and then there'll be a panel of industry folks and researchers who'll talk about what's to come. Is that a fair description, Mark? Okay. Good. So lots of things happening. This is the week after next on energy and super. Thank you.
So importantly, one of the things that's not happening the week after next is the energy seminar. So in the place of this Wednesday meeting that you're now at, there are those two events. Okay. So we will not meet at this regular time 2 weeks from today. So anyway, today's presentation is going to be by Chris Field, who's from the Carnegie Institute, and he is going to talk about the carbon emissions, past, present.
Thanks a lot. Well, as many of you know, when I give presentations, I usually talk about what happens to ecosystems and people when climate changes. But I want to step back today and talk about what's happening to the emissions, both the human drivers of emissions and to the way that natural ecosystems are responding to those, and use that to frame some issues about where emissions are headed in the future, and in closing, a few comments about how the new discoveries about the way emissions are changing now look like they're going into the future should reshape our thinking about managing carbon emissions. But before I do that, I want to just say a couple of things about the role of the Intergovernmental Panel on Climate Change, because there's been a lot of discussion recently about whether the conclusions from the IPCC are too conservative, whether they're watered down, whether they miss important parts of the science. And I think that once people understand the way the IPCC process works, it becomes clear that the answer is yes, the conclusions are very conservative, and yes, they have to be that way in order to serve the goals that the IPCC was designed to meet. The first thing you need to know about the IPCC is that it's intended to be a comprehensive assessment. The author teams are responsible for reviewing all of the scientific literature that's relevant to a particular topic, and it doesn't matter where it comes from or what the conclusions are. It has to be reported in there in a way that's consistent with the whole body of the science. It's an assessment and not just a categorization of the results, and so it's the responsibility of the IPCC process to evaluate the science. And that comes into really sharp focus when you look at the way that the IPCC chapters are reviewed. The chapter that I was responsible for, the writing team in the last assessment had an assigned length of 25 pages. The way the process works, that once the first draft is completed, it goes out to anyone in the scientific community who views him or herself as an expert and wants to provide comments. The comments on that first draft amounted to 175 pages, each of which had to be responded to individually by the author team and addressed in the chapter. And not only did each of those 175 pages of comments have to be responded to individually, but they had to be a response that was comprehensive enough that it passed muster with an independent reviewer who had nothing to do with the chapter except to say whether or not the comment addressed the substance of the concern. After that layer of review, there was a new draft that went out again for review, this time to all the world's governments, that had both their scientific experts and the people who were involved in the policy side providing comments. That results in another 175 pages of comments, each one of which has to be individually addressed and individually approved by this independent review editor. So by that time, the document is pretty thoroughly scrubbed, and there really isn't much left to assess in terms of whether the science is really a comprehensive report of what's out there in the literature. But the final approval process is the thing that makes you realize how the process has to be so conservative. And essentially what happens in the final stage, the plenary approval of the summary for policymakers, is in a room like this, representatives of all the world's governments gather, and they look at the document word by word. This doesn't mean, in principle, they look at it word by word. It means that government delegations, most of whom are political appointees and not scientists, look at the first sentence in the document and they consider the first word. Then they consider the second word, and there may be an hour argument over whether the second word is probably or very probably. And then they move to the third word, and every word in the document is thoroughly scrubbed. And the consequence of this is when the summary for policymakers is complete, and one of the key features of the summary for policymakers is that every word in it is tied with a very clearly identifiable chain of links back through the individual chapters that the governments have bought in. Every government in the room has approved every single word. All the world's governments are represented. The governments that are most enthusiastic about aggressive action on climate change, the governments that are most unenthusiastic about action on climate change. And every sentence has to pass the review of even the most skeptical of the world's governments. So if Kuwait or India or Saudi Arabia has a problem with a single statement, it doesn't get in there. So you can see from this that only the most thoroughly validated and the most the most thoroughly accepted statements are going to make it at all. It's amazing to me that anything can get through a process like that. If you ask what kind of a statement could you get through the U.S. House of Representatives where you had to have 100% consensus approval, you can take it from there. But my feeling is that this process of consensus approval has led to a level of acceptance by the world's governments that's really been responsible for all of the action on climate that we've seen so far, and for the prominence of climate in the current political discussion at the international level. And my firm feeling is that it's the IPCC process, which was really conceived by Bert Boleyn and a number of the other people who worked with IPCC in its very early days, beginning in around 1988, are responsible for the IPCC being a worthy recipient of the 2007 Nobel Peace Prize. And I think it was a fortuitous development that Al Gore emerged as a wonderful communicator at the same time that the IPCC reports really had the validation of the underlying science that was basically incontrovertible as a result of the original process. So this results in a very conservative set of documents, and I want to use that to frame where we are with emissions. And essentially the data that I want to be discussing are captured in the trajectory of the atmospheric CO2 concentration at the Mauna Loa Observatory here since continuous observations began in just over 50 years ago in late 2007, and over which time the concentration of CO2 in the atmosphere has increased from about 315 parts per million by volume to just over 380 parts per million by volume. Over the next 40 minutes or so, what I'd like to do is unfold this curve in terms of what it's telling us. And in particular, I want to focus on work that's been conducted by an international group called the Global Carbon Project, which is, this is a little walkthrough acronym soup. It's a project of the Earth System Science Partnership, ESSP, which is a consortium that is a result of joint effort by IGBP, the International Geosphere Biosphere Program, Diversitas, the International Program on Biodiversity Science, IHDP, the International Human Dimensions Program, and then one of the most unfortunate acronym choices ever, WCRP, the World Climate Research Program. And the fundamental data that I want to talk about is, this is a summary of where we were at the end of 2006. The atmospheric CO2 concentration is 381 ppm, about 100 ppm higher than it was at the beginning of the Industrial Revolution. Fossil emissions in 2006 were 8.4 billion tons of carbon. That's 35% above the level in 1990. The rate of increase from 2000 to 2006 was 3.3% per year, which was nearly threefold the rate of increase during the previous decade. This dramatic increase in the rate of CO2 emissions was reflected in an increase in the rate of growth in the atmosphere, which over the period from 2000 to 2006 was about 30% greater than the rate from 1990 to 2000. The challenge that I'd like to take us through is understanding why this rate has increased so dramatically and what it says about where we're headed in the future. I'm going to focus in this presentation almost exclusively on CO2 from the combustion of fossil fuel, and there are two reasons for it, but the idea that it's the only important greenhouse gas is not one of those. If you look at the IPCC summary of current radiative forcing, the forcing of climate change by CO2 is just about the same as the total net anthropogenic forcing, but that's not because all the other gases are unimportant. It's because all the other gases that are changed as a result of human activity include some that are important positive forcers of climate. Methane, N2O, and the halocarbons are a big factor, but there are also some that have resulted in negative forcing of climate, net cooling, and that includes land uses and the direct and indirect effects of aerosols. It's also important to note from this figure that the current assessment is that there has been a small positive forcing of climate from solar output, but that's currently only about 5% of the forcing from elevated CO2 in the atmosphere. The other main reason that I want to focus on CO2 emissions is that there's one important feature of CO2 emissions that makes them overwhelmingly challenging to deal with, and it's that there has been historically a very strong relationship between fossil carbon use per capita and per capita wealth. This relationship spans nearly 2 orders of magnitude of fossil carbon use, going from about less than 1/10 of a ton per year to almost 10 tons of carbon per person per year, and it spans an almost equal range of per capita wealth, going from about $500 per capita per year up to almost $50,000 per capita per year. This is a log-log plot, but if you look at a diversity of countries, a diversity of time periods, pretty much everybody falls along the same line. And what we would like to be able to figure out is a way for individuals and countries to move to higher per capita GDP without moving up this line. The history is mixed. If you look at where countries were in 2004, the world's important developing countries, India, China, are close to the line. The US is almost exactly on the line. There are a few countries that are substantially below the line in terms of using less carbon per unit of GDP. Japan and Switzerland are down here. And there is some good news in the pattern. If you look at the historical trajectories, for example, the US since 1980 has barely grown in per capita CO2 emissions. But basically, we really haven't figured out a way for a country to move from low levels of wealth per capita to high levels of wealth per capita without marching up this trajectory of CO2 emissions. And that's the technical and scientific challenge that we face, is how to enable countries to move this way without also having to move that way. Here's the history of carbon emissions from fossil fuel combustion going from the middle of the 19th century until the present. And you can see that things really took off after about World War II, that had increased dramatically. Since then, the total emissions are shown in the black line here, solid in the yellow, liquid in the green, and cement production and gas are the blue and red respectively. What I'd like to do is zero in now on the range of possibilities for the future. And essentially what that means is we'll start with this current around 8 billion tons of carbon per year and then ask where we may be going from here. And the IPCC has explored this with a series of scenarios. And you can think of these scenarios as internally consistent storylines. They basically characterize assumptions about rates of economic activity, about levels of globalization, levels of technology that are applied to problems, population growth. But they take advantage of historical connections between, for example, population growth rates and GDP growth rates to characterize a range of possible storylines. And the storylines range from this A1 fossil intensive shown in the solid red is one that looks pretty much like the world of today. It's a world of rapid economic growth, lots of globalization, and emphasis on fossil intensive fuel sources, all the way to A1T, for example, is a world with rapid globalization, the same economic growth rate as A1FI, but with an emphasis on non-emitting high technology energy sources. And you can see that it peaks in terms of emissions about mid-century and then gradually declines after that. But there are a variety of other kinds of worlds that are represented in these scenarios. B1, for example, is a world with lots of emphasis on local solutions, very little globalization, but it also has a heavy emphasis on wealth generation through service economies and high technology. A2 is an important one shown in the gold here. This is the most pessimistic of the scenarios that was considered in detail by the fourth assessment report of the IPCC. A2 is kind of a nasty world with relatively little globalization, slow economic growth, a lot of emphasis on protecting resources, and it ends up with very high levels of inequality among different countries. Now, these scenarios that we've used to characterize what the future might look like in terms of climate change were first published in 2000, and we've now had 8 years of experience with what the actual trajectory looks like relative to the projections from the IPCC. And one of the things we would like is that the history over the last 8 years has actually stayed somewhere within this range, and in particular between the highest scenario explored in detail, the yellow one, and the lowest. So here is zeroing in on the period from 1990 to 2010 for the same set of scenarios. The actual emissions are shown here from two agencies of the U.S. Department of Energy that report emissions. The reporting is mostly based on national statistics, but it can be cross-correlated against statistics from energy companies, for example. And as one would hope that until the IPCC scenarios start, the trajectory tracks exactly what the emissions were. But then things kind of fell apart. If you trace the actual emissions from 2000 through 2005, based on both reporting systems, the actual emissions quickly went to the top of the reporting of the scenario range. It's unclear whether this is really outside the range. It's not 100% clear whether this is a historical anomaly or whether we're really on a fundamentally different trajectory than those we've been considered. Looking at the 2006 emissions gives you a pretty good sense that the world is on a fundamentally different trajectory than those that have been considered in detail. Remember, this yellow one is the highest one for which we have good estimates of climate change. What that really means is that in only the first 6 years of tracing our way through these scenarios, we've already moved substantially outside the range of possibilities. One of the depressing consequences of that is that in terms of climate change, we really are operating in unknown territory. We don't have climate change simulations that explore the kinds of forcing that we're applying. I'm not in a position to say that over the next few years we're not going to see an economic meltdown that's going to push emissions back into that range of possibilities that's been considered in detail. But what we've seen over the last 6 years is that we moved aggressively out of that range. And what I'd like to do now is talk about why that is. But I want to highlight that the reason that range is important is that that's the way we've characterized the amount of climate change that we expect. This is the IPCC summary of surface warming as a function of time, and you can see the scenarios that have been considered in most detail. I apologize, IPCC used a different color than I did, so they've switched the A2 from gold to red. And what we're actually seeing is emissions that are running substantially above the A2 emissions, and we don't really know what that implies for climate. But it also is really important to recognize that there is a strong relationship in the data that are available to date between the amount of warming that occurs and the amount of emissions that occurs. The process that I want to use for thinking us through what's caused the recent increases is to partition total CO2 emissions into three terms. The first term is the carbon intensity of economic activity, how much CO2 is released to yield each dollar of GDP. The second is per capita GDP. These are basically the two terms I showed you in the plot earlier. And the third is the human population size. And we can partition the CO2 into this in a way that I think you'll find instructive. Here is the detailed trajectory of CO2 emissions from 1980 to 2005, and you can see that it almost precisely tracks the growth in global population. It also almost precisely tracks the growth in per capita GDP. What that implies is that there must have been improvements, decreases in the carbon intensity of GDP that have occurred through most of this period, and in fact that's been the case, so that what we're seeing is an almost one-for-one offset between increases in per capita GDP and decreases in the carbon intensity of the global economy. The problem, however, is that it's not 100% clear that we're continuing on those trajectories, and in particular I want to focus on the time since 2000 when emissions have really spiked, and what it looks like is that improvements in this carbon intensity of the GDP have either stalled or even reversed. If we look at different parts of the world, it's clear that carbon emissions are increasing everywhere. There's no place in the world where emissions are decreasing. In the US, they're increasing at about the rate of population increase. In the former Soviet Union, they decreased dramatically after the breakup of the former Soviet Union, but now they're back to increasing. And I'll come back to this later, but if you look at India and China that have had the most dramatic economic growth rate shown by the rapidly rising green lines here, you can see that carbon emissions have completely spiked. And this is especially true in China where, well, the line basically goes off my chart in only a few years of time. And a consequence of this is that we think that in 2007, China probably became the world's largest emitter of CO2, even though on a per capita basis, it's still only about a third of the US level. Here's a way to sort of think about the CO2 emissions as in a historical context. So cumulative emissions are about 75% a consequence of activities in the world's developed countries. The US, Europe, Japan, the former Soviet Union account for something like 75% of cumulative emissions since the beginning of the Industrial Revolution. But if you look at the total flux since 2000, you see a picture that's quite different. The developed economies only account for about 60%, with China becoming much more important and the developing countries becoming more important than that. If you focus on how much emissions grew from 2000 to 2006, you see a period that even shifts more emphasis to the world's developing countries, so that the developed countries are only responsible about 30% of the growth in emissions, and the other 70% are largely due to China, India, and the rest of the developing world. The way I think about this is that this cumulative column pretty much tells you who's responsible for the warming that's occurred to date, and this growth column pretty much tells you what kind of technologies we need to enable people to, reach their legitimate aspirations in a way that's not damaging to climate. And it's clearly the places where emissions are growing now, or even more realistically, it's the places that have the most people. And when you put it in this context, this is global population. The developed world is only about 20% of the population, and the other 80% is this rapidly developing countries plus the world's least developed countries, which become important in this scale. And I think this is really the highlight of where the solutions need to focus. I want to switch gears slightly now, and I want to talk about what's happened to the carbon that's been emitted, and then I'll come back and stitch these two themes together. There's another important source of carbon emissions over the last couple of hundred years, and that's that's the clearing of forests. Most forest clearing is now happening in the world's tropical countries, and it's more or less evenly split between the tropical Americas and tropical Asia, with tropical Africa leading to less deforestation. That number is about 1.5 billion tons of carbon a year reflecting forest removal from something like 13 million hectares. This 1.5 billion tons of carbon per year is only about 20% of the rate that's coming from fossil fuel combustion, but it's a not trivial component. It also is one of the ones where it's most feasible for us to make short-term progress. If we look at the history of fluxes from deforestation, we can see that from the beginning of the Industrial Revolution, most of the deforestation was occurring in the middle latitudes of the temperate zone in North America and in Europe, and following about World War II, deforestation shifted so that it's now almost entirely in the tropics. What I'd like to do over the next several slides is fill in this space with the sources of CO2 emission above the line and what's happened to those emissions below the line. And that gives us a feel for whether or not natural ecosystems are responding stably to the way we've changed the atmosphere. So fossil emissions started out in the middle of the 19th century as being a minor component of total fluxes. Fluxes from deforestation dominated until we were well after 1900, but fossil fuel fluxes have increased dramatically since about 1940, with a small but non-trivial contribution from cement in the dark gray here. Essentially, this is the amount of flux, this is the dark line here, that's just the mirror image of the one above the horizontal line, and this represents the space, the total amount of emissions we have to understand what happened to. And we have pretty good records of how much is in the atmosphere. We have extremely good records since 1957 from the detailed recordings at the Mauna Loa Observatory and now from a bunch of other stations. And we have good records of atmospheric CO2 from ice cores and other proxies going back much farther back than 1850. The question is what happened to the rest of this. This atmospheric fraction represents between 40 and 50% of this total emissions, and the other half we know has been taken up, at least temporarily, in the world's oceans and in soils and plants on land. We have increasingly powerful tools for partitioning this land and ocean uptake. We have increasingly powerful tools for understanding the processes that are controlling that. And our best estimate is that the partitioning of this extra uptake between the oceans and the land is shown here, with the oceans in blue and the land in the darker green. And there are a couple of things that are dramatic and important about this. The first is that both are important contributors to total carbon storage. And the second is that the ocean is a much more, let's say, reliable contributor to carbon storage, with the land varying from almost nothing in some years to very large amounts of carbon sink in other years. Essentially what's happening is that the amount of carbon going into the oceans is controlled by the effective concentration difference between CO2 in the air and the CO2 in the water, and that doesn't change dramatically from year to year. On the other hand, the CO2 flux into ecosystems is strongly controlled by regional changes in ecosystem processes. And in particular, what happens is during an El Nino, you end up with dry tropics, lots of wildfires, and carbon emissions from those areas, and typically a very small carbon sink as a consequence of that. The question that we'd like to ask is, does it look like land and ocean sinks are continuing to do their job in terms of taking up this 40 to 50 to 60% of the total CO2 emissions, or are we beginning to see signs that they're either strengthening or weakening? One way to look at that is just to say, well, has the fraction of CO2 that stayed in the atmosphere changed through time? If the atmospheric fraction is increasing, it means that as a fraction, the land and ocean are becoming less effective. If the atmospheric fraction is decreasing, it means the land and ocean are becoming more effective. The atmospheric increase on an annual basis is really spiky, but since accurate CO2 recording began at Mauna Loa in the mid-50s, we can see that there's a gradual increase in the fraction of the CO2 emitted that's remained in the atmosphere. It's increased about 10%, from about 40% of the annual release in 1960 to about 45% in 2005. Because this time series is so spiky, it's hard to say whether or not this is a significant trend. The most recent analysis we did said that if you're willing to accept a probability that it's a result of random error as high as 11%, then there is a significant trend, and it's been a 10% increase overall. So what's happening, or is there one part of the land or ocean that's weakening and as a consequence resulting in an increase in the atmospheric fraction? And what it looks like is that we're seeing decreased carbon uptake in the world's oceans at a rate of something like 0.4% per year. We're seeing a declining effectiveness of ocean sinks. Land, land is so spiky that it's not really obvious that there's any trend one way or the other. There has been a lot of evidence that severe droughts, especially since 2000, may have converted the land into something that looks more like a net source, but certainly the long-term time trend doesn't have any signal at all from land. What's responsible for this ocean fraction going down? What appears to be the case is that this is a consequence of two factors that are interacting. One is the disappearance or the weakening of the Antarctic ozone hole, and the other is global warming. Essentially what's happened is that those two processes together have tightened the vortex of winds around Antarctica, and these faster winds have basically been blowing the low CO2 water away from the surface and allowing higher CO2 water to come up to the surface, resulting in a decrease in the amount of carbon that's taken up in these high latitude waters. And it's approximately a 30% decrease in carbon uptake in the Southern Ocean over the last 20 years. So ideally what we'd like to be able to do is look at this spike in CO2 emissions since about 2000 and say, well, how much of it is due to the change in the carbon intensity of the world economy, how much of it is due to changes in land and ocean sinks, and how much of it is just due to increasing economic activity. So one thing we can do is skip one. No. Oh, well, let's say, so this is the partitioning we want to do. And let's look at the trend in carbon intensity. A reasonable way to say, well, how much has this reversal or stalling of the improvement affected this spike, is to just do a linear regression through the historical time series and say, well, how much is this difference? And if we take this difference and multiply it by the per capita GDP, you end up with a contribution to the total emissions. And that ends up to be approximately 17% of the extra emissions since 2000. If you say, how much has the change in the atmospheric fraction affected the extra emissions since 2000, you can come up with a reasonable way to do that by just taking the trend times the time interval times the total emissions, and that comes up with the increase in the airborne fraction explaining about 18% of the excess emissions since 2000. When you put all three of these together, it turns out that about a third of the extra CO2 growth rate since 2000 as a result of changes in the carbon intensity and the increasing airborne fraction, about 2/3 as a result of increasing economic activity. And as I said, the basic problem is that we really haven't figured out a way to grow economies at the same time that we're not growing CO2 emissions. The dashed green line on this figure shows where the world would have to be at 1/4 of the current CO2 emissions for a given level of economic activity, or alternatively, how you could increase economic activity fourfold without increasing CO2 emissions. And essentially, this represents the magnitude of the problem that we face moving forward for the next 50 years or so. The challenge is to have the world economy move either horizontally across this graph or ideally diagonally downward and to the right. Here's a way to think about the size of the challenge. Most assumptions say that in 2050 we're going to be looking at a world economy that's on the order of 4 times the size of the current one, with carbon emissions in 2050 that are no more than current. That basically means we need a 4-fold improvement in carbon intensity, or we need to get down to the dashed green line on the last figure. An even greater challenge, though, is that by 2100 we're probably looking at a world economy that's anywhere from 10 to 20 times the size of the current one. And most of the assessments to date have said that we're going to need to do that at carbon emissions that are no more than about half of current. So we need to figure out a way to improve the carbon intensity 20 to 40-fold. I want to close with a discussion of how we need to think about stabilizing emissions in order to stabilize climate. And the basic, I forgot one other figure that I wanted to mention, just to highlight the size of the challenge. The current global energy use, as you know, is about 15 terawatts. And if we continue to grow emissions at the rate of global economic growth, which has been around 3% per year recently, then basically that 3% growth means that we need to be looking at adding the equivalent of 450 gigawatts every year, or 450 big new power plants, just to stay at where we are in terms of emissions. If we can continue the past improvements in carbon intensity, which we don't seem to be doing, but if we could do that and get 1.5% per year improvements, that would cut that number about in half. But it still means that the challenge that we face is how to get to the stage where we're building the equivalent of 225 big new power plants with no carbon emissions. Okay, so the final thing I want to talk about is the question of, when we talk about stabilizing climate, what are we actually talking about stabilizing? And I'm going to switch gears from talking about these Global Carbon Project results to talking about the results that are in a new paper in Geophysical Research Letters by Damon Matthews and Ken Caldera. The paper is on the website, is in press now, and it comes out in the next few weeks. And the basic theme of this paper is that we've tended to think about what do we need to do to stabilize CO2 concentrations in the atmosphere. Stabilizing CO2 concentrations in the atmosphere is a difficult problem because you need to dramatically reduce emissions. But if what you're trying to do is stabilize CO2 concentration, you still get to emit some CO2 going into the future, because the CO2 that we emit is gradually removed by the uptake in ecosystems and the ocean. This is a scenario from this paper that uses a coupled carbon climate ocean model to explore the fate of CO2 that's emitted to the atmosphere. And the results that they show are consistent with ones from lots of other models. If you release a big pulse of CO2 to the atmosphere, it's gradually absorbed in the ocean and ecosystems over the very long time period. Approximately 80% of any CO2 pulse is going to end up in the oceans. And that removal is relatively slow. About 50% is removed in a century, and 25% or more lasts over 5,000 years. The new insight from this Matthews and Caldera paper is that this gradual drawdown of the CO2 pulse by land and ocean uptake doesn't really help you if what you're interested in is stabilizing surface temperature. And the reason that it doesn't is shown here. Essentially what happens is that as the CO2 concentration is pulled down by ocean and ecosystem uptake, the ability of the ocean to take heat out of the system is going down at about the same rate. As a consequence, even though the CO2 concentration is going down, the surface temperature increase really isn't going down. So what does that mean? What that means is that in order to stabilize climate, we don't need to find a way to keep emissions going at the level where they're replacing uptake in the sinks. What it means is we need to find a way to cut emissions all the way to zero. Here's an inverse calculation that illustrates that. This is for 3 levels of equilibrium temperature increase. I'm sorry, there 4 degrees, 2 degrees, and 1 degrees, and for 3 rates of temperature increase, 0.4 degrees per decade, 0.2 degrees per decade, and 0.1 degrees per decade. And the calculation that Matthews and Caldera did is they said, okay, so how much do I need to emit in order to really stabilize temperature at these 3 different levels? And this is cumulative emissions from 2000 over a period of 500 years. And what you can see is that for each of these 3 levels of warming, and for all 3 of the different warming levels, you end up with cumulative emissions that have to be capped, and capped in such a way that there's no long-term growth. And this is a reflection of the fact that if there's any emissions, what you're ending up with is that yielding an extra increment of forcing of climate, because the CO2 removal is basically being matched by the decrease in the ability of the oceans to take up heat. Okay, where does this leave us then? It leaves us in a situation where we know fossil emissions are increasing rapidly. They're increasing rapidly mainly because global economic activity has increased, but they're also increasing rapidly because some other important things are happening in the carbon cycle. In particular, carbon intensity is stalled, or it's actually eroding. We're seeing that the ocean carbon sink is weakening, and we're seeing that the growth rate of atmospheric CO2 is increasing as a consequence of not only the rapid economic activity, but also the stalling of the carbon intensity and the weakening of the ocean sink. And then finally, the new insight from this Matthews and Caldera paper is that if our long-term goal is stabilizing climate and not just stabilizing CO2 concentrations, we need a way to figure out not how to stabilize CO2 concentration, but to reduce CO2 concentration emissions to zero. This is where I want to close, and I think that these 5 conclusions highlight a really important broad set of challenges. A lot of the work at Stanford and a lot of the work that all of you are doing is focused on finding ways to transition us to a non-CO2 emitting economy. I think the bottom line from these 5 conclusions is a really simple one. It's that however hard we were working, now we have to work twice as hard. With that, I'll stop, and I'd be glad to take any questions.
Potential wrinkle here. Hansen has recently said that 350 parts per million, or 1 degree Celsius of total felt forcing, might be the limit of Greenland, and that occurred in 1989. And what I'm curious about is your thoughts on a strategy, collective thought towards drawing down the CO2 in the atmosphere and making that equally as much of a priority as reducing current emissions based on carbon intensity or economic activity.
Thank you for turning those on, but my personal philosophy is that the solution to this problem it's got 4 major components. Actually, it has 5 major components: conservation, efficiency, new technologies, capture and storage, and that we've got to adapt to the changes that we can't avoid. There are a whole bunch of attractive ways to remove CO2 from the atmosphere, and I think that they need to be pushed. I haven't personally seen compelling evidence to indicate that they're going to be the complete solution to the problem, and I think they need to be viewed as part of a package that includes all 5 of these components. If there's a single message that comes from watching the trends in carbon emissions over the last decade, it's that waiting around for these new technologies to develop is a big mistake, and that what we need to be doing is focusing on the things that are going the wrong way now, and that as each of the opportunities come forward in these areas, we should be taking advantage of as fast as possible and not waiting.
Does that mean that the market system is really too weak to make that?
It doesn't necessarily mean that. If you wanted to see the market system deal with this, you'd have to get rid of the subsidies that are encouraging utilization of fossil fuels, and you'd have to find some way to put a price on carbon that was realistic and meaningful enough to drive solutions into the marketplace. I guess the thing that concerns me the most about the kinds of market solutions that have been discussed is that I think they're typically discussed as operating on a time scale that's slow relative to the rate at which the problem's changing.
I guess I didn't understand what you said about stabilizing climate versus stabilizing CO2. In the pre-industrial world, we had a certain amount of CO2 emission, and we had a certain stability in our climate. So if I stabilize CO2 in the atmosphere at some level, I'm going to get some equilibrium climate. And you confused me a lot with those last few.
Okay. Well, you're exactly right. We did have an equilibrium level of CO2 emissions in pre-industrial. It was approximately 0. There was maybe 1/10 of a billion tons per year average emissions from volcanoes, which is about the rate of mineral formation at the bottom of the oceans. And so I think the key take-home message from that is that with zero emissions, you get zero climate change. That's the pre-industrial, that's where we need to go in any post-industrial climate.
But I took it in a different way. There's a certain constant CO2 in the atmosphere, and that left us with a constant climate. So why, if I stabilize CO2 in the atmosphere at some new level, don't I get a constant climate?
So the basic idea is that as we force the climate with excess CO2, we're ending up with a continuous forcing of climate. That's resulting in a rate of temperature change that reflects the partitioning of this extra heat between the water and the ocean and the atmosphere. If we have a greater concentration of CO2 in the atmosphere, we're forcing the concentration harder. But as that concentration is pulled down by the CO2 moving into the ocean and into ecosystems on land, the ability of the oceans to take up the forcing of temperature by the CO2 that remains is going down at almost exactly the same rate.
What causes that?
Why are they matched like that?
What causes that change in the heat uptake?
It's basically because the water that's coming up to the surface has already been warmed by past exposure. No?
So I was going to ask a related question. So the Matthews and Caldera paper says what happens if we can stabilize emissions. But if you look back to where you started to the IPCC scenarios, and you look at continued increases in emissions, does the Matthews and Caldera piece suggest that we've underestimated the amount of warming that would be associated with those different CO2 increase scenarios, or are those kinds of feedbacks already taken into account?
All of the IPCC stuff I showed you only went out to 2100, and the real relevance of the Matthews and Caldera is in centuries after that, where hopefully we've figured out a way to no longer increase emissions, and where the concentrations are gradually being drawn down by CO2 uptake processes.
So what about other potential sources? Like I've read permafrost potentially is a big issue. There are others. You didn't mention any.
Right. Well, that's a whole other talk. From my perspective, the core challenge we face in dealing with climate change is finding a way to limit the amount of warming that occurs to the extent that we don't have land and ocean processes becoming a feed-forward mechanism where they're releasing enough CO2 as a result of the warming to drive future warming in a way so that even if we could cut off all human emissions, we'd still see increasing concentrations in the atmosphere. My group and many others are working very hard to figure out what that amount of warming might be, and we really don't know at this point.
The model CO2 record shows these nice annual cycles. So when you look at, you blew the data up on the atmospheric fraction, we showed a very non-periodic, we call it a spiky signal with periods that look like they're ranging 3, 5, 7 years. But it's over a time period where we have a lot of information about the Earth. One would think that there's the ability to model that and understand that complicated signal. Can you say a little bit more about what's going on?
Well, as I said, the biggest driver of the interannual variation in the amount of CO2 growth in the atmosphere is the size of the land sink. And the size of the land sink is most strongly controlled by whether or not you have an El Nino. When you have an El Nino, you tend to have big carbon releasing events in tropical ecosystems. And so essentially what you're seeing is the fingerprints of land processes transmitted to the atmosphere through the effect of large-scale climatic processes that are influencing the land processes. Bert.
Can you say something about the prospect of negative emissions to solve the problem you just laid out?
Well, so what are the technologies you might use for negative emissions? I mean, you could figure out some kind of carbon capture and storage mechanism where you weren't capturing fossil carbon, you were capturing biomass carbon, for example, and putting that into long-term sequestration. You can imagine a carbon capture system that was set up to remove CO2 from the atmosphere without having it involved in the fuel cycle at all. Klaus Lochner talks about that a lot. And, you know, in principle, there's no reason that those can't be parts of the strategy in the future. I think that what I see as the constraint is that going from nothing to having strategies implemented at a scale that really makes a difference is a multi-decade, multi-billion-dollar process, and without investments, we don't really have any idea of how likely it can be. Lynn?
So Chris, there's another whole set of arguments that we didn't go into regarding pH in the ocean, and yet changing pH in the ocean must, to some extent, influence biological uptake of CO2, and therefore export to deep ocean or some fraction of that. How does that feedback work? Does it help or hurt, or how does that work?
Well, you can think of the ocean CO2 uptake as having a fundamental control that's just the concentration difference between the air and the ocean, and the wave action is kind of it's an accelerator. And then there are a variety of pumping mechanisms that essentially decrease the concentration of CO2 in the surface waters. One is biological uptake, and to the extent that the organisms sink out of the surface layer, that's room for more CO2 to come in. Another is temperature control. Just the solubility of the CO2 is quite temperature sensitive, and of course, so warming works in the wrong direction for that one. For the biological pump, am I doing that? Well, maybe I should step away from the microphone. For the biological pump, we really don't know whether or not it's likely to increase or decrease moving into the future. And for the there's basically one other pumping mechanism that's related to the distribution of the carbon species between carbonate and bicarbonate and CO2. And that one's also likely to move in the direction of a weakening sink in future decades. So if you look at all of the ocean processes with a big unknown on the biological side, it's likely that ocean sinks will decrease in strength going into the future. For the land processes, the general consensus is that a relatively small fraction of the current land sinks are a result of CO2 fertilization, maybe 25%, and those might continue well into the future. We don't really know where the saturation level would be. The other 75% are mostly due to refilling of carbon pools that were empty as a result of human actions, and this is things like constructing reservoirs and letting carbon-rich sediments accumulate, filling landfills and filling up trash, regrowing forests that were previously harvested. And the 75% mechanisms are primed to basically fill up with carbon and stop accumulating. And the real big question is, how close are we to seeing pools of carbon that have been relatively stable become vulnerable? And that's things like the permafrost carbon. It's things like, will we see enough drying in tropical areas to convert previously inflammable forests to flammable ones? And will we see large changes in soil carbon in areas that are used for biofuels production, for example?
Just we should have maybe one last question.
Okay.
I was worried about this extrapolation 500 years into the uncertainties are tremendous. You can go to Hansen and he will tell you that you only have 20 years before you hit a tipping point, and things that inexorably will go down some path. And the spread is so incredible, and the slow feedback mechanisms, ice lines and things. I just find it very strange that one is attempting to go 500 years.
Well, if I were to predict, the stock market 500 years in the future, you should laugh. But if I'm predicting ocean turnover times or consequences of ocean turnover times, which are basically on several thousand years, 500 years in the future, I'm only going out a fraction of the turnover time. So, that's like saying, I bought a new car, I expect it to last for 10 years, how fast do I think it's going to go in 5 years? So it's true that this is a system with many different processes that are dramatic and important and operate on very short time scales, but it's also really important to recognize, and that's the reason I put these data up, that there are other processes that operate on longer time scales. And I think for the ocean turnover, the time scale of going out 500 years is actually an appropriate one for understanding these processes. That doesn't mean that that's going to be the only process that's operating over that time scale, but it does mean that that's a relevant time scale for understanding those implications.
So you were saying that I'm trying to understand, do you believe Hansen, or don't you believe Hansen when he's talking 500 years in the future? These are so radically different predictions that are happening.
Well,
and you're telling me that
I would say
it's
that
in a time scale that you do understand. So I'm asking, what is your prediction?
Well, first, I don't think I said anything that's inconsistent with anything that Jim Hansen says about risk to major continental ice sheets. I don't think I mentioned the word ice sheet once. And what I'm saying is that this is a dimension of the climate problem that ought to be on the radar screen of the scientific community as they grapple with the issues. Now, if we decide that 1 degree of warming is the maximum that's consistent with a sustainable future, what that means is that we need to figure out a way to reduce CO2 emissions to zero along the trajectory that I showed is consistent with 1 degree warming. If we decide it's 4, and Hansen's argument is 1, if we decide it's 4, it's still zero emissions, but on a different time scale.
Well, speaking of time scales, I think we've reached the end of ours, so very much, Chris. I'm sorry I have to I have to
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.